reason. Just a second, please. So here just animation I am showing. After that we will go to the class. So here when you combine P and N type semiconductor, in P type we know majority carriers are holes. Okay, these blue bubbles are like holes. Okay, red bubbles are like electrons. Okay. So left side we have P type semiconductor and right side we have N type semiconductor. In N type where minus sign is indicating acceptor atoms and plus sign is here donor atoms. Okay. So when you combine these P and N type semiconductors separately are connect means actually practically we will take one semiconductor, after that we will deposit another semiconductor, or we will take intrinsic semiconductor from one side we will diffuse phosphorus atoms, or one side other side opposite side will diffuse aluminum atoms, or third group. Okay, third and fifth group will diffuse from opposite ends, then it will make a PN type semiconductor. Okay, here also you can see the left hand side P type semiconductor and holes are the majority. Right hand side you have N type semiconductor and electrons are the majority carriers. Okay, these are here you can see these whatever acceptor atoms and donor atoms are immobile. They are not moving. They are fixed in a crystal lattice. These are immobile charges, immobile atoms you can say. Okay, here whatever free electrons, free holes are these are free. This can move freely within the semiconductor, right? When you combine this semiconductor, there is the interface. So after that, so because of the charge, please mute. Because of the charge gradient, because of the charge gradient, so electrons will diffuse from N type to P type, and similarly, while diffusing, they leave the positive ionized charge density near the interface. Okay, they are leaving electrons leaving behind positive charge density, that is plus charge here. This is due to donor atoms, that is phosphorus atoms or fifth group atoms, whatever you can say. Okay, from left side also holes diffusing from P type semiconductor to N type semiconductor because higher the concentration or density of electrons are higher than the density of electrons is higher than the density of hole. Sorry, holes is higher than the electrons. So these holes also diffusing from P to N, and these holes leaving negative charge behind these holes. Okay, this is negative charge. Left side is forming negative charge near the interface towards P side negative charge is inducing, and right side positive charge is inducing. This is due to acceptor atoms and donor atoms. Okay, this charge is this region we are calling space charge region or depletion region. Once this charge is induced here, there is a electric field due to this charge density, positive charge density and negative charge density. Okay, because of this charge density also, because of this electric field, we have a built-in potential or barrier, you can say barrier. Okay, once this depletion region is forming, there is a electric field. So electric field direction is always positive to negative. So this electric field, what this will do, this will stop the electrons and holes from N side and P side to cross the barrier. Okay, so this electric field, whatever this electric field, what this will do, suppose electrons are diffusing from N to P, so electric field direction also positive to negative. So this will stop the electrons in N side and N type only, N type semiconductor only, and holes and in P type semiconductor only. So actually it means there is a barrier. So to cross this barrier, the electrons and holes should have some energy. Then only they will cross the barrier. Okay. So indirectly, this electric field is stopping for the diffusion of charge carriers. Okay. This is the simple PN junction diode when you form the junction. Okay. So here see, only near the interface only this cross the barrier, because why the others are not crossing means here whatever near the interface electrons moves from N to P, there is a depletion region is forming. This depletion region is like a some barrier. Okay, because of this depletion region, because of this electric field, there is a potential barrier. When we discuss about band diagram, you will clearly understand this one. Okay, remaining electrons and holes, they don't have that much energy to cross this barrier. So this, for that we need to apply some forward bias and reverse bias condition. Okay, that we will see. Okay, this is just equilibrium conditions. Okay, now I think you understand how this will work. Okay, is it clear to you? If you have doubts, you can ask. Either could you follow this animation?
Sir, once again explain, sir.
Yeah, okay. See here. Here first, this is a p-type semiconductor. Right side is n-type semiconductor. N-type means fifth group elements, that is donor atoms. Okay, and electrons are there. In left side, p-type semiconductor means acceptor atoms, that is third group atoms, and free silicon material. Because of this third group and silicon are fourth group elements, third group and fourth group will get the p-type. P-type means there is a acceptor atom, that is here indicated minus charge, and free holes. These are blue bubbles are free holes. So if you see different if you see semiconductors separately, holes are freely moving within the semiconductor, and right side electrons are moving freely within the semiconductor. These are free, but these ionized acceptor atoms in p-type semiconductor and donor atoms in n-type semiconductor are immobile. This will not move because these are fixed in a lattice or fixed in a crystal. Okay, so when you combine here electrons, if you take n-type semiconductor, electron density is higher compared to hole. Holes are very less, very negligibly small. Okay, and in p-type semiconductors also, these blue bubbles, or you can say holes, are higher compared to electron. So because of the charge gradient, because of this high density, electrons will diffuse from n to p side, n-type semiconductor to p-type semiconductor, and holes will diffuse from p-type to n-type. Okay, that we'll see. Okay, now they diffused. While diffusing, they leaves the positive charge density near the interface. This is positive charge density. You follow my cursor here. Okay, left side, these holes diffuse from P to N. Then they leave a negative charge behind these holes. Okay, this is near the interface only. Okay, because of the charge density, we are getting some electric field in this region. This region we are calling space charge region. Also, you can say depletion region. Depletion region means after forming this positive and negative charge density, there is the electric field. This electric field, what is doing? This electric field sweeping the electrons holes from this small region. This region, whatever this space charge region, already free electrons holes means free. This can move anyway. Okay, this depletion region, this electric field is sweeping the electrons and holes to other side. There is no very less free charge carriers. That's why we are calling depletion region. That means deplete the charge carriers from this region. Electric field is the job of electric field is here. So it is depleting the charge carriers or sweeping the charge carriers from this small region. So once this region is forming, the other electrons only, whatever having higher energy only, they cross this depletion region. So which are not have that much energy, they will not cross this barrier. And indirectly this electric field is stopping the further diffusion of charge carriers. It is stopping the further diffusion of charge carriers. That is why you need to apply some forward bias and reverse bias depending on our requirement. Okay, this is this is the formation of uh, PN junction diode. I will explain again. No need to worry. Okay, that is to just you explain in a animation form. Then you may understand clearly. So we'll see here again. Okay. See, I will take a bigger diagram. Okay, already we discussed several times. So anyway, we'll do same whatever animation you have seen. Now you will understand here. Okay, this is P type and N type semiconductor. Here P and here N. Here we have N type means fifth group atoms and fourth group atoms. Here electrons are the majority carrier. So electrons are the majority. You can say, you can take like this. These dots are electrons. Okay, you consider these are electrons. Here holes are the majority, right? So what happens? These holes are majority. This will diffuse into the entire semiconductor and leaves here a negative charge density. This negative charge density due to acceptor atoms. Acceptor atoms means third group atoms. Okay, third group atom. These are acceptor atoms. Okay, here also these electrons will diffuse to n-type p-type semiconductor and leaves a positive charge density. Okay, this is donor atoms are fifth group atoms. Okay, so this leaves here this region like this. It will form a positive region, positive charge and negative charge. This region we are calling a space charge region. Just we have seen in the video also. Okay, animation also. This is the space charge region. Because of this positive and negative charge density, there is a electric field. That is, it is internal electric field, and you can say direction is positive to negative. Because of this electric field, there is a built-in potential or VBI, or you can say built-in voltage or built-in potential, that I will explain while discussing band diagram. Clearly this will understand. Okay, so after this one, at an equilibrium condition, or because of this electrons will diffuse this direction, electron diffusion, and holes diffuse in this direction, right? Holes. So after this electric field is forming, electric field direction is positive to negative. So here this electric field, this will stop the remaining electrons to diffuse into n-type semiconductor, and also holes also diffusing from P to N. It will stop. Okay, and only this is the equilibrium condition. Okay, this is the only whatever charge carriers. This is interface here. What do you say? This is interface. Whatever charge carriers are free electrons holes only near the interface only diffuse. After that, this junction is forming, or this barrier is forming, or depletion region is forming. This depletion region is forming. So this remaining electron want to cross this region, but there is a barrier height or potential. These electrons should overcome this barrier, then only they will enter into p-type semiconductor. Only whatever some of the electron may have some energy, then only they overcome this barrier. Otherwise they will not overcome this barrier, and they will remain stay in the n-type only, and holes also remain stay in p-type semiconductor only. So this region we are calling depletion region. Why? Because this electric field sweeps the remaining. Suppose here free electron is there, free hole is there. This electric field sweeps the this remaining this electron and hole. Okay, that means this region is having very less number of free holes and electron. That's why we are calling depletion region. This region is depletion region. Okay, so this is the thing, and it is a in equilibrium condition. There is no flow of this will continue. This diffusion of electrons and holes will continue up to equilibrium condition. That means equal number of diffusion of electrons, holes will be there. There is no further diffusion. Here also suppose 10 electrons are there. Here also some 10 electrons are there. So this concentration is equal. Then there is no further diffusion. Here 10 holes are there. Here 10 holes will diffuse. After that there is no diffusion of holes. So there is no diffusion of holes. That is the reason in equilibrium condition there is no flow of electrons. That's why we will apply some forward and reverse bias condition. Okay, forward bias and reverse bias condition that we will see. Okay, so I will draw here at a time forward, reverse and equilibrium condition. Then you will clearly understand. Okay, let's take a little bigger diagram. So this is the interface, you can say. One more diagram I am drawing to comparison. You will able to understand this one. Here one more diagram I will take. Okay. So then when you compare this three zero bias and forward and reverse bias, you will able to understand. This is the interface. Whatever I drawn line. This is interface. This is p type and this is n type. So in forward bias, suppose this is zero bias. Okay, zero bias means we are not applying any external voltage. So here there is a depletion region. Here you can say depletion region is forming. Already we have discussed here positive charge, here positive charge, here minus negative charge. Okay, here so this is zero bias, then there is no flow of, here electric field is moderate, electric field will be there. Okay, here electric field, internal electric field, this is internal electric field is moderately there. Okay, now here we are applying forward bias condition. Okay, forward bias condition, that means this terminal is connecting to, or you can say this terminal is connecting to negative potential. Okay, this terminal is connecting to positive potential. Okay, this is positive potential. Because of this positive potential, holes having positive charge and this positive potential, because of this positive potential, these holes will repel and these holes only move towards the interface, whatever holes move towards the interface, and these electrons are negative charge, and here we connected this n-type semiconductor connected to negative potential. So this negative potential is repelling these electrons, and electrons will not come towards this direction, only electrons move towards the interface only. Okay, so like that, when hole is combining with negative acceptor atom, this will becoming a neutral atom, suppose. So that's why here depletion width is reducing in p types in forward bias condition. Okay, in forward bias condition, what happening? So holes are combining with acceptor, ionized acceptor atoms. This negative acceptor atoms are there in the depletion region. These holes are combining with negative acceptor atoms, and this becoming a neutral atom. This region is called neutral region. Whatever this is depletion region, this is also neutral region. Neutral region means what? What is neutral region mean? What does it mean? Neutral means there is equal number of electrons and protons, that is neutral region. Okay, so here also this positive charge and positive charge density is there. We are sending one electron. So because this positive charge, there is a again neutral charge, neutral region is increasing. Neutral region is increasing. This neutral region, just a second. So here this positive charge density, ionized charge density receiving one electron, and the here suppose two let's take two ionized atoms. Okay, here also negative and negative. So when we convected forward bias, this depletion is reducing by, why? Because positive ionized density receiving, or positive ionized donor atoms receiving electron, and this will becoming a neutral atom. So neutral region is increasing in forward bias condition and depletion region is decreasing. So suppose here see, left side 4 charges are there, right side 4 charges are there, 8 charges are there. So here internal electric field is higher compared to here, because charge density is reduced in forward bias condition. Now here we will apply reverse bias condition. That means negative potential is connected to P terminal and positive terminal is connected to N terminal. Because of this one, this positive potential attract the electrons towards the terminal, and also this negative terminal attracts holes towards the negative terminal. Because of what is happening, more number of atoms, acceptor atoms are ionizing here. Okay, more number of acceptor atoms are ionizing here. Okay, like this the depletion region it is increasing. Similarly, inside also more number of donor atoms are ionizing. So electrons are leaving these donor atoms. So that's why here depletion region is increasing in reverse bias condition. So suppose here a atom is there, phosphorus atom is there. Once electron is leaving here, so what we will get? P plus we will get, right? P plus region we will get. Like that, here charge density is increasing. That means electric field is increasing in reverse bias. In reverse bias. So you see these three diagrams very clearly. So in without biasing, only whatever electrons are higher density in n type and holes are higher density in p type. So this will diffuse because of charge gradient. We are not applying any external biasing. In forward bias condition, what happening? Forward bias condition means p type semiconductor is connecting to positive terminal of the battery and negative potential is connected to n type of the semiconductor. So because of this one, what is happening here? And in n-type semiconductor, let's take n-type semiconductor. In n-type semiconductor, electrons are the higher concentration, right? So these electrons is repelled by this negative potential, and because of the repulsion, these electrons only moving towards the interface only. That's why when electrons will interact with ionized donor atoms, this will become a neutral atom. So that this depletion region width is decreasing in inside. Similarly, same thing happens. These holes will repelled by positive potential and holes will move towards the interface. And here also neutral region will increase. Holes will interact with acceptor ionized atoms, that is aluminum atoms or third group atoms. Then the depletion region or ionized atoms are reducing here. That means depletion region is decreasing in this p side also. So totally in forward bias condition, depletion region is decreasing. Depletion region decreasing means charge density in the depletion region also decreasing. Because of this decrease in depletion charge density, internal electric field also reduces in forward bias condition, right? Only in forward bias condition, diffusion is the main process. Takes place. Okay. So we will come to the reverse bias condition. In reverse bias condition, what is reverse bias condition means? P-type semiconductor is connecting to negative potential of the battery and n-type semiconductor is connecting to positive terminal of the battery. So because of this one, positive terminal is attracting these electrons because it is positive is connected to n. So electrons are not moving towards the interface. Electrons are moving towards the positive terminal. That means more number of electrons will leave the donor atom. Leaves the donor atom, and this donor atom is more ionizing because electrons are leaving this donor atom. Similarly, same thing happens here also. Holes are attracting towards the negative potential because the holes having positive charge. Like that, negative charge density is increasing in p side and positive charge density increasing in n side. That's why depletion region is increasing in reverse bias condition. Because of this increase in reverse bias electric field, there is built-in potential also increase. That we will discuss when we discuss band diagram. You will understand what is potential barrier, that we will see. Okay, because of this electric field, uh, because of the increased charge density in the depletion region, this internal electric field also increase. Okay, here because of this increased electric field, only minority carrier electrons will drift towards the n-type semiconductor. Minority electrons will drift towards this n-type semiconductor because electric field is increased. Electric field direction is always plus to minus. So minority carrier holes in n-type semiconductor also drift towards the n-type semiconductor holes. Minority carrier holes. This is drift process is prominent in reverse bias condition. So why holes are drifting here? Because this electric field opposes the electron to diffuse. Diffusion of electrons is opposing by this electric field. Only this electric field will push the holes. Holes are the minority carrier in n-type semiconductor. These holes are drift moving, or these holes are traveling or propagating from N to P side by electric field only. This is why here drift process is prominent process in reverse bias condition, and diffusion is the prominent process in forward bias condition. Okay, so this is in forward bias, depletion is reducing and internal electric field also reducing, and in this process diffusion is the dominant process. In reverse bias, depletion width is increasing and charge density also increasing. Because of this one, built-in potential and internal electric field also increasing, right? Internal electric field also increasing. So in this reverse bias, drift process is dominant process. Drift is the dominant process. Okay, is this clear to you? At least clear this one.
Yes, sir.
Three different forward, reverse, zero bias condition. What is the difference?
Sir, it is connected to battery.
Yes, yes.
Okay. That's it.
Yeah, battery only. Battery here we connected. Why internal electric field is increasing means here see. So already external field direction is what here. Suppose in reverse bias condition, here we have connected negative and this positive terminal is connected to this p-type semiconductor, right? Right. So here external field direction also, how it is direction? In this direction only. External, this is external field direction. This is internal field, this is external field. External field means C. So here battery is connected, negative potential is connected to P, positive potential is connected to N. So electric field direction is in this direction, right? Minus and plus. So resultant field, electric field is increasing. Resultant, this is total or resultant electric field is increasing in reverse bias condition. But if you take forward bias condition, what is happening? Forward bias, if you take P type and N type is connecting to negative potential, right? And P type is connected to positive potential. And if suppose electric field, internal electric field is in this direction, internal electric field, but here direction is in this direction, external, this is external. So in forward bias, internal is in this direction, this is internal, and external is in this direction. So external, this is, so resultant electric field will decrease here in forward bias condition. In forward bias condition, external field direction is opposite to the internal field direction. Because of this one, total electric field will reduce in forward bias, but in reverse bias, this total electric field will increase because this external field and internal fields are in same direction. That's why here electric field is higher in reverse bias and drift process is dominant in reverse bias condition. Okay, in diffusion process is dominant in forward bias condition. So why we are applying forward bias, reverse bias means in zero bias only up to certain concentration only. After suppose here you have a two regions here you have two regions, here 20 electrons are there, suppose here 0 electrons are there. So after, because 20 electrons are there, these are diffusing to this region to this region. After 10 electrons reached here, in both regions we have same number of electrons. In that case, there is no further diffusion of charge carriers because equal number of charge carriers are there. That's why, so there is no flow of electrons and holes. That's why you need to apply forward or reverse depending on our requirement. That's why we are studying this forward and reverse bias also. Okay, is it okay to you?
Yes, sir.
Yeah, okay, now we'll see very important thing, band diagram. That is also very important. So if you if they ask forward by PN junction diode, how the form